Last week, I gave a survey of particle physics around the year 1968. Today, we would like to discuss you okay skating? And then MIT SLAC experiment, and then Feynman's pattern model. Okay, so those are the topics of today's lectures. Now, in 1909, Rutherford did an extremely important experiment which establishes the model for atom. And we are all familiar with such a model. The electric charges, positive charges are centered in the nucleus, and then the electrons will circle around this nucleus. So this is a nucleus. Now we know that this nucleus is made of nucleons, and the nucleons means protons and neutrons. And hopefully today's lecture which confirm for you that these protons and neutrons are made of quarks. So this is today's topics. Now, in 1962, that was exactly 50 years ago, I knew that SLAC. SLAC means Stanford Linear Accelerator Center. Was established and this year there was a celebration, the 50th year celebration of this new lab, okay? And a new experiment, it's called electron nucleon scattering. This element is either the proton or neutron. And it started to, the experiment began around 1967 or so. And it's very similar to what what the Rutherford did for the atoms. It's like this. You have an electron, and then scatter out another electrons, and then this is a photon with a momentum q, and then you have a proton, for example, with large momentum p, and then this. So the final state n, and there are several things. One is that this electron-proton scattering, because electron doesn't have strong interactions, so the interaction can go through electromagnetic interaction. And then the coupling constant E squared over 4 pi is called a fine structure constant, is 1/37. So it's very small. So one can use the perturbation, in particular one photon exchange, to describe this process, and that will be good enough. And the other thing is that this n, no restrictions. So anything came out will come out. So this is called a totally inclusive. Reaction. If you restrict yourself to proton in the final state, that will mean the elastic scattering, but this is anything. So this is inelastic. Now there are several kinematic variables. So the kinematic. One is q squared, but because of this is scattering, that this q squared is spacelike, and in the Joachim-Drill matrix, the q squared spacelike is negative. So let me call capital Q squared is equal to minus q squared, and this is bigger than 0, so it's spacelike. Then the other one parameter, the invariant variable is called, defined to be m nu. M nu is p dot q, a scalar product between p and q. And so you can see that in the rest frame, at the moment proton, then the p vector is equal to 0. Then in this equation just becomes m nu equal to, well, p equal to 0, then the time component will be just mass. So equal n, and then the q naught. So you see that the nu equal to q naught. And the q naught is just the energy transfer. So capital Q squared is the momentum transfer, and the mu is the energy transfer. Okay? And you can convince yourself those two, this one and this one, the only two Lorentz invariant variables you can construct in this process. Furthermore, we know everything here, above here, because this is a simple Dirac particle and so on. So all we study in this experiment is this part. And you can see that almost obvious that what you study here will be about the structure of this proton, okay? There are a few properties of this materials. For example, here P plus Q square will be equal to the event mass square of this final state, right? And because proton is stable, so this mass must be bigger or less than m squared. Whatever the final state is, there will be at least one neutron or proton. And so that describes this condition. So let's work it out. So for P squared plus 2P dot Q plus Q squared will be bigger than m squared. Now this is equal to m squared. So this m squared and that m squared cancel. And then 2P dot Q is 2m nu. And the plus Q squared equal to minus Q squared. So this is bigger than mu. And so this gives me 1 minus Q squared divided by 2m nu bigger than that. Okay? So I get a constraint on these variables. Q squared over 2m nu. It's obvious it's bigger than 0. And it's less than 1 because of this. Okay? So that's the range of variation for this ratio Q squared over 2m nu. The other interesting thing about this process is that this Q squared, it's the mass of square of this virtual photon. And this Q squared, unlike usual particle, it can be controlled because Q squared is the momentum transfer. By changing the momentum transfer, by looking at the outgoing electron in different directions, you will change Q squared. So Q squared is a variable. It's not fixed. And the Q squared is very similar to a resolving power. If you have a higher Q squared, then the experiment will explore smaller and smaller distance. So because Q squared is under control, you can control it. So this, you can change the resolving power of the experiment. And that's a very useful tool to understand the dynamics of these things, okay? Now, if you want to compute the cross-section, then this vertex will be just the electromagnetic current, Jmu. And that's the amplitude. But if you want to compute the cross-section, you take this and square it. So there will be 2 factors of Jmu and so on. So the differential cross-section we will have to compute this kind of things, J mu and N, J mu and P. Here's P. And then you put a 0 here, okay? And then you have to supply the overall energy momentum conservation, P plus Q minus Pn, and then just put the 2 pi factor, 4 pi here for convenience, and then you have to sum over all ends. Okay, so eventually what you have to do is that you have to you need this tensor. This will lead to W mu nu. And then this will be the function of the two variables q and p, and that equal to d for x e to iq dot x, and p j mu of x, j mu of 0, and p. And then there's a spin average, which I did not indicate the spin average, because the proton can have a spin up or spin down. Okay, now you can find many derivations how you go from here to here. Essentially, you take a delta function and then write it as d4x eq, momentum like this, and then use the Heisenberg equation of motion to relate the j mu of x and so on. Look at this. If you have trouble, you can look at the 郑大培、李凌峰 the book. Okay. Now, for historical reasons, I put the 4 pi squared e p over m. Okay, like this. Now, I'm using the old-fashioned normalization of the states like this, and that's why I need these factors. Okay? Now, because of current conservation, we have j mu d mu of x equal to 0, okay? And this turns into I q mu by integration by parts. Look at this. So that means q mu W mu mu mass range. So that's the condition for current conservation. So the W mu mu can only have 2 structures which satisfy this condition. And then one of them is G mu mu minus Q mu over Q squared. Okay? And historical reason that I put a minus sign here. And then the other one is 1 over n squared p mu minus p to q over 1. I think it's q squared. Q squared. Q mu, and then you have p mu minus p of q over q squared q mu. Okay? And then you take q all into these things, then this vanishes, and also the q mu also. And the coefficient of this is called W1. And the coefficient of this is called W2. And then once I took out the tensor structure like this, the only dependence of this W1 and W2 can only depend on scalars. So it can only depend on Q squared and mu. And this and Q squared and mu. Okay? Okay. Then what you have to do is take any textbook on quantum field theory, plug this in there, work out the cross section. I'll just write down the cross section for you. energy, did I, oh yeah, here. The instant energy is E, and the energy is E prime. Okay. And then P cosine theta, and cosine theta is you have electron coming this way, and then the outgoing electron going that way, and this scattering angle is called theta. And this formula go to A pi alpha square Q square, and then the final energy of the electron square, and then I have 2W1 sine square theta over 2 plus W2 cosine square theta over 2. So this is the formula for the inclusive electron nucleon scattering, okay? And it's a very famous formula. Okay, so that's the electron scattering. How about the neutrino scattering? I talk about. We would like to derive some rules for neutrino some rules. So the similar thing you can derive this way. You have a neutrino, and then for example this will be an electron, for example, and then you don't have a photon, so there's some kind of a contact interaction here, and then you have a proton here, and then you go to anything at the end. So it's very similar. So let me just write down the formula for you, and this formula is the following. The corresponding tensor for W mu nu like this. For the neutrino scattering, it's a very similar tensor here. And the tensor is W mu nu, let me call it neutrino scattering curve, this. And then has a similar structure here, 4 pi squared E P over M. And then I have a D4x. E to I Q to X, and then a P, and then I have a J mu Hermitian adjoint, and then J mu of 0, and P. And the reason is that this weak current changes charges, so it's not neutral, so you have to distinguish between whether it's J mu or J mu Hermitian conjugate, okay? And for neutrino, it turns out to be this way. Now, similarly, this has many structures, like a G mu nu, W1 nu. Then I have P mu over M squared W2 mu. And then I have, let me explain this in a moment, okay? I have I epsilon mu nu lambda kappa P lambda P Q kappa. Over Q squared over N squared. And then W3. And then I will tell you what they are. Now, the weak currents are not conserved, so we don't have the structure of course, like, it has to be Q mu over Q squared on the other structure. Okay. Now the other terms here, these terms, and then this epsilon mu lambda here because of parity violation. Parity. So we have just an extra term, and we don't have it for the electron scattering. Now these extra terms vanish if we assume that the electron mass and the muon mass is equal to 0. Or usually we are talking about high energy scattering, so the mass of electron or mass of muon can be ignored, and under the limit we don't have to worry about this thing. Okay. So, in terms of this so-called structure functions, the W's, then I can write down for you a similar expression for the cross section. So I have B sigma mu E Q squared B mu will be equal to GF. GF is the Fermi coupling constant squared divided by 2 pi, and then I have an epsilon prime over epsilon, and then here I have 2 W1 neutrino scattering sine square theta over 2 plus W2 neutrino, and then cosine square theta over 2, and then I have E plus E prime over N, and then I have W3 mu, and then sine square theta over 2. Okay? So you can see that, for example, the first two terms almost identical in structure to the electron scattering. And this term is extra because of parity violation. Now, for this is neutrino scattering. If you have a anti-neutrino scattering, this will be exactly the same. And then W1, this will be anti-neutrino, and then it will be sine square theta over 2 plus W2 neutrino power, and the cosine square theta over 2 plus similar expression for this, okay? W3 and mu bar sine square theta over 2. And you can get B sigma of the anti-neutrino from the cross section for neutrino scattering by interchanging this J mu, J n, and J. Okay. You just interchange because the anti-neutrino, so you can change this to just the charge changes different signs, so you can just. The details are not important. What I want to do is to show you so now is the time to discuss the other sum rule. please ask questions if you have questions, okay? Now, I show you, not show, but give you the current algebra, right? Last time. And I'm not going to write down all the details, but just that the V and V, vector current and vector current will be equal to vector current. Sum of delta 3x minus 1, something like this. And then V A will be equal to A, and then something like this. And then if the actual current and the actual current are turned into V. Now, as I mentioned, that one of the motivation for proposing this current algebra by Gell-Mann was that this relationship are nonlinear. So this will fix the scale of the V current. So one motivation and motivation is to fix the scale of V current. As I mentioned, that because as you discover more and more particles, and then you will add up all the contribution to the V currents. But how do you normalize them? Well, this will tell you how to normalize them, okay? But as also mentioned, once you publish a paper, some smart and clever people will find other uses for these results. And that's what Steve Adler did. I forgot the year, probably 1960 something. I don't remember exactly, 64, 65 or something like that. Then it showed that this current algebra will lead to the following sum. Oh, here. W2 for the anti-neutrino, and then you have a Q squared and mu dependence for these structure functions. By the way, this W's are called structure functions. For obvious reason, right? Because this supposed to describe the structure of the target, the proton, so they're called structure function. And then for neutrino scattering, Q squared and mu, and this equal to 4 cosine squared Cabibbo angle. This cosine theta is not the scattering angle. This is the Cabibbo angle. Okay. So this is Cabibbo. Then the third component of isospin for the target, and then plus sine squared theta c 3. Y is the hypercharge plus 2, 2, 3. Okay. Now, I'm going to say that the details of this are not important. Just the fact that this is a constant, independent of Q squared. the fact that the right hand side, you see, on the left hand side I have integrands which depend on nu and q squared, two variables. But somehow if I integrate over nu, then the q squared dependence disappears, become independent of q squared. Okay? And that's the this is the important point. Okay? And I'm going to explain to you why it's interesting and important. Before I do that, I will have to make one more thing clear. You see, this is the neutrino scatterings. In the 1960s, there was no neutrino beams. Neutrino beam was very difficult to create at the time. But we have electron beams because SLAC is under construction. You will have a huge high energy electron beam will be available. So it's very difficult at that time to imagine that these sum rules can be tested in any near future because neutrino beams are not available. Okay? So neutrino beams available. So, what can you do? Well, it turns out that the Buchanan so this is a Buchanan. You know that the electromagnetic current has two pieces. One is I equal to 0, called isoscalar current. And then there's I equal to 1 current here. Okay? And so you have the product of J EM x J EM at 0 and this. Then you have two this Ji equal to 1 at 0 x Ji equal to 0 0 and then plus cross terms. Okay, Ji equal to 0 x and Ji equal to 1 0 and then plus Ji equal to 1 x Ji equal to 0. And then I have Ji equal to 1, and then I have Ji equal to 1, 0. Okay? Now, it turns out that the Buchanan was able to do the following. Then you take this P, J mu x, J mu of 0 for, let's say here, n. And let's take the average, sum over n equal to proton and the neutron. Proton. Taking the average. Then you will be able to cancel these two terms. These two terms will not contribute. Then this will just equal to Ji equal to 0, x Ji equal to 0, 0, or Ji equal to 1, x, Ji equal to 1, x, like this, okay? And each term is positive definite, so this is certainly bigger than n, Ji equal to 1, x, Ji equal to 1, 0. And then you take the sum of the neutron and the proton, okay? Then with this, it's in the isovector currents now. Then you can use isospin rotation. To relate this to the weak current. Because the weak currents are the ones that, it's V1 plus IV2 or something. It's the isospin current, but in a different component. And this one, you can use the isospin rotation to relate this to that, okay? In any case, by making these manipulations, Biot was able to derive an inequality. So, W2 for EP, Q squared mu, was W2 for E neutron, Q squared over mu is bigger than 1/2. Okay. Okay. Now, the 1/2 is the following, that if it's 1, well, let me just say, this is the value of 1/2 is half of the point length spin 0 charge party. But half is not important. So this means that this integral is comparable to a point length cross section. And this is the crucial point of the sum rules. Okay? Okay. And the beauty of this inequality is that this refers to electron scattering, and the slag is already preparing to do this electron scattering. So this inequality can be tested right away. And compared with the neutrino, this is a much easier way to do it, okay? So that's the Biot's first contribution to this. Now, why this is so important? Well, let me explain to you why. The slag experiment here leave the final states arbitrary, inclusive. Any state it can come out of this experiment, they will come out. Now, before this experiment, they have done it before. They have done the elastic scale. That means that you have E going to E prime, and then you have photon here, it's a proton, and then this is also a proton. Okay, nothing else, just a proton with a momentum now. And here, because of structural function, that this has a form factor here. And then they discovered that, or they measured the form factor, okay? And then if we take this will be part of the final state of this. You just restrict your final state to be the proton. Then in that case, it has a contribution to the W2. So you have a Q here, and here's a P and a Q prime. So we just look at what's the connection? Q plus P squared equal to P prime squared. So that equals M squared. So equal to Q squared plus 2Q of P plus M squared equal to M squared. So M squared cancel. So Q squared plus 2 mu equal to 0. Okay, so for this process, Q squared and mu satisfies this condition. So if you calculate what's the corresponding W2 for this process, you'll find that W2 Q squared and mu will have a delta function which tells you that the Q squared and mu are satisfies this condition. So you go delta Q squared plus 2 mu. And then when you square this amplitude, you have a form factor, another form factor, so you get the form factor squared. So like this, okay? Maybe there's some numerical factor, but that's not important. But what they found was that the form factor for large Q squared is go like 1 over Q squared for large Q squared. Okay? That means this is a rapid drop-off. So the contribution to this integral here from the elastic contribution will go like this. mu2 W2 EP elastic Q squared and mu will go like 1 over the Q to the 4th. Okay? So very small. Now, at the time, before the experiment for total inclusive cross-section, people made some estimate of what the cross-section should look like. And then because of this rapid fall for the elastic form factor, there's from the elastic contribution very small, and then they argue that for inclusive. Okay, so this is expectation. All you have to do is just include a few resonances, contributions. And what kind of resonance? A star, or all kind of things. And each one, we know the form factor is very small. So they thought that even if you include some resonances, the contribution to this sum will be still very small. Okay. I think I would like to take a 5 minutes break now. And then when I come back, I'll tell you that the experimental result totally disagree with this expectation. Okay.所以又回到 Buchanan， 那 Buchanan 他要解释这个问题。那他对他来讲，这样就中文词。To Buchanan, the most important point about this Q-square independent is that when Q-square is very large. Because, as I explained here, oh yeah, here. The cross section is very small when Q-square is very big, okay? And so, if Q-square is not very big, then he thought that was not very remarkable. What's remarkable is this. So what he proposed to do is this. Rewrite this integral as this. Okay? Let's call this integral I. And then define called f x q squared is equal to mu w2 q squared and mu. Okay? And x is equal to q squared over 2 and mu. And then you remember that this variable is between q squared over 2 and mu is between 1 and 0. I think you remember this range, kinetic range is this. Okay? So instead of mu, I can use x as my new variable. Then I will be equal to dx 0 to 1, and then f x q squared is a q squared independent. Then he just made a proposal. Stating a proposal. So this function f x and q squared, as q squared become very big, then this will become function x. That's the Buchanan scale. Okay? And then this integral becomes very simple. I equal to f 0 to 1 dx f x. And then of course it's q squared independent. So the argument is very simple and naive. Okay? And so this is the famous Buchanan scaling prediction. nu W2 Q squared and nu becomes Q squared bigger with infinity, just becomes function Q squared over 2nu.
From his inequality, it is still consistent. If Q squared goes to a very big value, then the integral grows up. It's still consistent with the inequality, right? So
You mean if the integral blows up?
right.
Yeah,
So
but
the large Q squared.
yeah, but it doesn't blow up. The worry is it will become very small.
Okay, from the
Yeah, from the elastic cross section, just is that this integral will become very small.
Okay.
When large Q squared is very big, then this become very small. That's the main worry.
Okay.
Nobody worried that this will become infinite. It did, but the worry is in the other direction. Okay? So, this, and because it's like, I explained to you, it's like a point like a cross section. So this suggests that the proton is made of point like constituents. Okay? And from this integral here. Now, the Slack experiment point like constituents. So it's a product is some constituent. Oh, 看不出来结论了。Because the integral goes like one, goes like here.
对啊，这样子为什么一定是 point like constituent?
Well, if it's not point like, then if each one is it's a huge thing, it will go like this. They will have a huge form factor, it will go to 0. At that time, the people were two pictures. One is like a proton is like a, what do you call it, jelly? And it's very soft. The other one is like a point like constituent. It's very similar to Rutherford experiment's conclusion. If you have a huge cross section, then indicate that this object has a point like a constituent. Give you a point like a cross section. If you don't have a point like constituent, then each one has a substructure, and they will give you a form factor, and the form factor will show you that the cross section will become very small.
我的意思是说，
Yeah.
我的意思是说，你不一定非要 point like 不可，
Otherwise, like
说
what?
不定有别的可能性。
Well, that's the.
至少从这个 argument 来看的话，这个 argument 还没有秀出来说，这个一定是 point like particle 的形式。
It's very suggestive. it's let me say it this way.
当然，我们知道说，这个结果可以秀出来，这个原来的form factor 等等，
没有，
对不对？
没有 form factor。
对，这个不对嘛？
呀，没有 form factor 就是 point
对
like 嘛。
但是并不代表它一定是 point like。
不是，这个没有 form factor 就表示是 point like。If you have a form factor, if a particle has a form factor, it means it has structure. It's not a point like.
有一点对，
Yeah.
这一点我同意。
Yeah. Okay. Yeah, I also agree with you. The argument is not very rigorous. Yeah.
The bound in this inequality is coming from current algebra.
Yes.
I would think the current algebra didn't assume that there are point-like particles.
Did you say did or did not?
Didn't. So
Well, that's everybody was surprised. Somehow you did not think the current algebra assumes the point-like constituents, but somehow the current algebra implies them. And I don't know why. Okay. Now, the slack data. This was in 1968. The Panofsky represent the data in the Vienna conference. And it shows two things. One is that your cascading, and the other is that the magnitude is comparable to point-like cross section. Okay. Now, I told you that I finished my PhD in 1968, and I went to SLAC in the summer of 1968. My original offer, the appointment, the starting point was September. But as you know, a graduate student very poor, and I wanted to make more money. So I asked SLAC whether I could go earlier than September or not. He said, okay, come. So I went there in July. And then, let me take a piece of chalk. So, finally, and the purpose for his visit was every summer, SLAC has some kind of camp for disadvantaged children. And during this camp, they always invited a very famous physicist to give lectures to these poor kids to encourage them to do science and so on, okay? And finally went there to give these lectures. But as you know, when you have a very famous physicist visiting a laboratory, all the experimentalists wanted to talk to you, to tell them what the data and so on. So all the experimenters talked to him, and it turned out that it's very interesting. Because finally, before the visit, he never heard of electron scattering, this experiment. He never heard of this W1, W2 structure functions. So the experiments will tell him, your W1, W2, a new W2 has a Biot scaling. He will say, what's W2? What's Biot scaling? So he kept asking questions. Then in one afternoon, of course the farmer is very smart, so he figured out all these details. And then in the evening, he just invented this pattern model in one evening. And the reason one of the reasons, of course he's very smart, but one of the reasons he was so quick was the following. At the time, he was doing a PP schedule, cross collisions. But you cannot do very much in a PP collision, because if you draw a Feynman diagram, you have a P, you have another P, and then because of strong induction, all you have is a big block. And then, so you don't know what's in here. You cannot disentangle the structure from this one or for that one or something. So he just got stuck. He didn't know what to do. Okay. So when he was told of the electron scattering, then he was so happy, because half of this amplitude here is totally known. So the only thing you don't know is this. So everything here will tell you the structure of this problem. So in some way, it's already half the problem solved. All you need to do is look at the structure of this. Okay, and that's why he's so excited. After he learned this experiment, he gave an analogy. Is how to study the interior of the watch. Probably some of you heard the story, right? Well, he said the one way to do it is to take a watch here, and take another watch here, and just hit each other, and hoping that the watch will break, and then you can see what's inside. That will be something like this. The other way to do is take a watch and open the cover and shine the flashlight and look at what's inside. And that will be it. So that's his analogy of this watch-watch collision. Now, okay, so let's talk about Parama. Well, we don't need this anymore. Now, there's some preliminaries I have to tell you without proof. It says the following, that you take a proton here, and then assume there are lots of constituents inside. Okay? Then you go to coincident momentum frame. Then in this frame, you can show that all particles, all constituents, move forward. If it's in a raised frame, then you see that some particle can go this way, other can go that way. But if you go to the infinite momentum frame, then all the particles move in the same direction. Okay. So if you take each one of Pi, then you can write the Pi equal to Xi as P. And then the Xi will be positive, and it becomes 0 and 1. That's just a statement of this. Some of you, if you learn quantum field theory in infinite momentum frame, then you may find this statement like that, okay? And then sum of Xi will be equal to 1. Let's just say that all the momentum sum up to the total momentum, okay? The reason he says that he wants to go to infinite momentum frame is that imagine this is an old-fashioned perturbation theory. Then, because of time dilation, that each individual intermediate state will live longer because of time dilation. And when it lives longer, especially compared with the this virtual photon, when the virtual photon hits all of them, will be have a big impact. But the impact will be very short compared with a lifetime. And then during the period, then this continuum can be thought of as free, as a free body. And that's his intuition like that. Okay? You may not take his word for it, but that's his idea. So if you have this, let's take this one. So you have a photon, Q goes like this, and this is a Pi, and this becomes Pi prime, okay? Then if you look at this vertex here, you will see that, okay, let me, Q plus Pi squared equal to Pi times squared, okay? That's just the energy momentum conservation. And then you write it out, the Q squared plus 2Q dot Pi plus Pi squared equal to Pi times squared. Now the idea that these constituents live quite long compared with the Q squared, the impact, means that this Pi squared and the Pi times squared is very small. Compare with Q squared. And in the modern language, it means that this is off-shelfness. Is small. Okay? So let's take this expression here. And then Q squared, according to here, is a minus capital Q squared. And then let me say that Pi is equal to Xi times P. Look what I have there. Then this will become 2Xi P dot Q. And plus Pi squared plus Pi times squared. Okay? So let's move the Xi. So move Q squared and the other to this side. So 2Xi P dot Q equal to Pi equal to capital Q squared plus Pi prime squared plus Pi squared. Okay? And 2P, this is equal to 2 and mu Xi. equal to Q squared plus PI squared P prime. This is a minus. That doesn't matter, but just keep it away. Okay? So you can see that the xi equal to Q squared divided by 2n mu plus 2n mu Pi prime squared minus Pi squared. But as I said, that the argument that these particles are almost live as free particle means that this is, and that's very small. So we can drop this. So this is very small. And so this becomes xi equal to Q squared divided by 2n mu. And that's essentially Feynman's particle model. It explains two things. One is that this Q squared over 2n mu, the scaling variable, measures the fractional longitudinal momentum. Okay? Because this xi is it's a fractional longitudinal momentum of the particle. Okay? And the other one is that this structure function measures the longitudinal momentum distribution. Because the structure function will measure this, what's the probability of this particle with a momentum fraction xi. So the particle model, Feynman's particle model, gives these two interpretations. One is scaling variable, the other is the structure function itself. And the experimenters were very happy with this, because before, the structure function W1 and W2 are mathematical objects. To them, it did not mean anything. It's just some quantity which appear in the cross-section. Here, Feynman gave an interpretation that this function measures the momentum distribution. And the other is that when Biogen proposed the scaling, the Q square over 2n mu just a scaling variable. It did not have any simple physical interpretation. And Feynman's particle model gave an interpretation. This precisely is the fractional momentum which the photon hits a particular particle. Okay. So now the experimenters can go home and use the intuition to think about this cross-section in these pictures. That's why it becomes so popular. Okay? Now,
对，Feynman 这个 invention
yeah.
有点从无中生有的，对不对？
Yeah, you can say that. Because you check, if you want to verify or confirm whether what he said was true or not, you'll find that you cannot do it.
对啊，他尤其他要 P 变成无穷大，
Yeah.
为什么会想到 P 要变成无穷大？
Well, I don't know, but at that time,
一开始就给了嘛，
啊
他一开始就说必要的道路这么大嘛。
，Yeah，他这个，you know, at that time, Weinberg and some other people already have studied the quantum field theory in the infinite momentum frame, and then they make this kind of
但是不是
yeah,
不是
but
Feynman 啊？
不是 Feynman, but I doubt Feynman knew.
你那时候也在研究这个啊？
Oh, that was after I learned from Feynman, so I tried to
再回
learn.
去。
Yeah, oh, no, I didn't start before it.
Oh yeah.
Yeah, I suspect he's talking about this idea was because he was looking at the PP scatter, and the most natural frame to do is PP scattering in the center of mass frame. So each one will have a very large momentum, and he's a type one of them. So that's my guess. I'm not sure. What I was going to say. Oh yeah. As I mentioned that Feynman visited SLAC not long after my arrival at SLAC, and one day during his visit, I usually went to work about 9:30 in the morning, and I noticed this SLAC's green room was full of people, and I wasn't sure what was going on, so I entered the room, and it was standing room only, and I noticed Feynman was explaining his ideas to everybody about his invention of Part 1. So that was a very exciting time. Oh, and one thing, you know, this was 1968, and the idea of quarks was not generally accepted. Lots of people did not believe in quarks. So Feynman wanted to make sure that his model is more general than quarks. So he insisted call this patterns. Patterns just, you know, this is a part, and I put on here. So he said that patterns are not quarks. So to give it more general possibilities. But of course that all the theories right away say that patterns are quarks. And the reason for their this idea was the following, because if patterns are not quarks, then you don't know their quantum numbers. You don't know what's the charge, what's the isospin, what's the, but you know that the quarks are the patterns, and then the quarks you know the charge, the hypercharge, isospin, everything. So all the quantum numbers are known. Okay, so not only the electron scattering that you can get some prediction, but also the neutrino scattering, anti-neutrino scattering, because the quarks, the quantum numbers are known. So how a quark is scattered from a neutrino, you know how to do it, and therefore you get many predictions. For EP, electron, neutron, also neutrino P, neutrino, anti-neutrino P, and so on. All this you can write down lots of predictions. Now, at the time, there was no neutrino beams, but because of this, experimentalists started to design neutrino scattering, and then within a year or two, they did the scattering, neutrino scattering, and then they confirmed all these predictions. So within 1 or 2 years, it's really went very fast. Many predictions. Okay. Now, then, because Parton model was very successful, yeah. For me, how do I pronounce it? Phenomena. So some very serious theories. They want to investigate if fibers so lots of really serious theories wanted to study whether the Parton model idea was correct or not. So they started to compute this W1 and W2 in model field theory. And then they all discovered that Feynman's idea didn't work out. There are always logarithmic violations of scaling. And they did not know how to handle those logarithms, okay? And this was because before operator product expansion, before renormalization group become popular. So there are two groups of theories. One just emphasized the phenomenology, and they work out all kinds of details. The other one was a very pure theorist. They said that the Feynman's Parton model cannot be correct, must be wrong. So they didn't believe it. So there's always a fight and debate going on like that. And what I want to do next time is to tell you the story how it. But before I do that, let me mention two applications of the Parton model. So let me just mention two applications. And one is E plus E minus going to difference. And the Parton picture will be E plus, minus, the photon, and then create a Q quark pairs. And then this quark pair will just decay later, okay? So all you have to do is how to compute the cross-section for E plus E minus going to Q quark pairs. And you can compare this with the E plus E minus going to mu pair. the cross section for this. I think it's, yeah. GQ squared, okay? So sigma E plus E minus going to hadrons divided by this ratio. Mu plus mu minus. You just look at this picture, the only difference is that we just say mu plus mu minus. The only difference is charge here, right? So this equal to E I squared and sum over I. I is the quarks. Then, if you just have a U, D, and S, that's people knew about the quarks at the time. Then this is a third charge. This is minus 1/3. That's minus 1/3. So this sum over I of charge I squared will be equal to 2 over 3 squared plus 1 over 3 squared plus 1 over 3 squared, and that's equal to 9, 4 plus 1 plus 1. So that's equal to 2/3. Of course, at the time there was no data to compare this with. Then it turns out that this one doesn't have no color. So if you include colors, then you this ratio, or this ratio is called R. Will equal to 2. Because you multiply by 3. And a few years later or actually quite a few years later, in the 1970s, then this number is confirmed. Okay? So that's another indication that you need a color quantum number to explain everything. Okay. The other application is usually known for Troyan, but I feel a little bit embarrassed to call my own name. This is a mu pair adaptation. In the PP position. So you have P plus another product, then I put a mu plus mu minus plus anything. And this experiment was a Letterman did this experiment. In a book. And Joel and I was looking for another process which we can use a pattern model to describe it, okay? So it turns out that if you have, say, P going this way, and another P going this way, then suppose one of this particle here go pi, and this is go pi prime. And it turns out that if these two annihilate into a new pair, then this process can be described by this pattern model. So I don't think I'll go to the detail. It just turns out that when the mass, the mu pair mass, is large. Then you can do this. Maybe I'll do, so this is Q. Okay. So let's do in a central mass system, okay? So this P this way and the P go that way. So in the central mass, then the total energy S is P plus, okay, P is P, 0 P, and then this P prime is P 0 minus P. So this is energy and that's momentum. Energy and momentum. So the total energy is P plus P prime squared. And then you look at that, so it's equal to 4P squared. Now here, the PI will be equal to x1, let's call x1 P. And this PI prime for x2 P prime, okay? So Q squared equal to Pi plus Pi prime squared, right? Yeah. So you can see that if I write it out, this will be equal to what? It will be equal to x1 P 0 P, and this will be equal to x2 P 0 minus P. So if I sum these two up, this component and that component will add up. So that will be equal to x1 plus x2 P squared, and this one and that one will take the difference. So it will be equal to minus x1 minus x2 squared P squared. So if I work it out, then you see you get 4x1 x2 P squared, and 4P squared is S, so that equals x1 x2 S. So I get a relationship that the Q squared over S is equal to x1 times x2. So the cross-section for this new pair production depends on the momentum distribution of this target, the momentum distribution of this target, and they are related. The fractional momentum are related by this x1 times x2 equals Q squared S. Okay? And this process turned out is very useful in in the machine design. For example, when they wanted to build a machine to produce W and Z's, they have to know what kind of parameters you need for the machine so you can produce enough events for the experiment. And this process will give you this. And then of course the compute the cross section for new particle. So for this process, it was useful in the W and Z discovery, and even the Higgs too. Okay, so that's the second application of this. Okay, so next time I'll tell you the story. It's a very fascinating story how people discover asymptotic freedom, and it's a step by step. It includes many theories with many different ideas, and then finally become possible to find asymptotic freedom. Okay, so that's the next section. Thank you.